is a professor in computer systems at Uppsala University, Sweden. He has an MSc in electrical engineering and a PhD in computer science, both from ETH Zurich. His research interest is in wireless systems, ranging from system design to energy efficiency and security. Professor Christion was the lead architect for the Haggle opportunistic communication platform and is a board member of IoT Sweden. So the keynote title is Battery Dynamics and Battery-Free Communication in IoT, that is Internet of Things applications. Over to you, sir.
So thank you very much for the invitation to give this keynote to you. And before I tell you about energy efficiency in the Internet of Things and about the very timely topic of backscatter communication, I would like to show you where I'm coming from. So Sweden is in the north of Europe, and Uppsala is about as close to the polar circle as you are to the equator. That means that we have very long days in June and July and very short dark days in December and January. Then we have snow and ice, but that's not only something scary, it's also fun. We still ride the bicycles, or we do ice skating on the lakes, and if we are lucky, we can see the northern lights on the sky. So, independent of where we are in the world, we see the trend that we get more and more connected and have a digital society nowadays. Everything from industrial to consumer products, they get equipped with small embedded sensors and computation capabilities. Now with that, we can sense the environment or the surrounding of these sensors. The devices can interact with it, and then together with all this information that is collected, we can build smart applications that hopefully are very helpful for us to organize our lives and in industry, and you basically build up very smart environments, goods and services, as you might have heard or seen some examples before. Now, from an architectural point of view, every physical object has a virtual representation somewhere in a data center. So we have an update on this sensor. This update is sent and put into the records in a data center. Likewise, if we change the state of a virtual object of an actuator, this will be synchronized with the physical device itself, and in this example, maybe switch on the light bulb or change the colors if we change some values in the data center. So by combining these physical virtual objects, we can build very powerful applications. One example, the trivial example shown here, is that if the sensor senses that it's dark in the room, we lighten up it. But we can also take into account and combine these applications with information services and social context from the internet, and thereby building really rich applications around us. Now, the Internet of Things is not something that is the future. It is actually already here, and we are about to use it in our daily lives and are already surrounded by a lot of connected devices. There are still a few challenges to get there. One of the biggest challenges is security and privacy. You can imagine that if you have a lot of sensors that can sense the environment, we are also part of the environment, and therefore the system will learn about a lot of our presence and how we behave. Because of the large number of devices, we talk about 20 to 50 billion of devices. This is also very attractive to make attacks to the internet infrastructure, for example. So we need mechanisms that help us to better protect these devices and also to over time develop a better understanding and intuition what security in the Internet of Things actually means. Another challenge is the large amount of data that is collected from these sensors. This amount is expected to exceed the capacity that we have in the Internet very soon. And to approach this challenge, we start to do data aggregation and processing already on the devices as much as we can. Often these devices are a bit resource constrained, but still we can do quite some filtering and data compression to help not overloading and congesting the infrastructure. And what I want to talk to you about today is the energy aspect of the Internet of Things. We are already very busy with charging our mobile phone now and then. And now imagine if we have to charge all the other devices that are maybe owned by us or surrounding us. This is not possible. Also, I think it's the responsibility of us engineers and computer scientists to build sustainable applications and systems. If we look where the energy is spent, then we need some energy, obviously, for the sensing. Now, taking a temperature reading doesn't take as much energy as doing a chemical analysis of the air quality, or even taking pictures and doing some basic image object recognition already on the device and send it to the cloud. Then we have some computation that helps us to coordinate that how this device should behave in a bigger system, to both, as I already mentioned, compress data, maybe filter out some data, and also coordinate the communication. And the communication is the third important building block in this IoT, on an IoT device. If we look on a typical power profile, that looks about this, that we see the communication is absolutely the most power-consuming component during the operation of an IoT device. Then we have also a bit of sensing, but actually most of the time our devices are put to sleep to save energy, and we are only operating at a very small fraction of time. This is called so-called duty cycling. Now, if we want to build energy-efficient systems, the state of the art nowadays is to do duty cycling, to sleep as much as you can, to minimize computation, both in the number of messages and the length of messages that you send, and to minimize computation. Now, this is not as easy as it now might look like, because the nodes have to operate in a distributed system. And depending how you interact with other nodes, if you use unicast or broadcast messages, or if you have a system with asynchronous wake-ups during these sleep times, then you have to coordinate and maybe wait until other devices are awake. So there are some challenges involved in making such a system energy efficient. And here are some traces about if you use unicast or broadcast. It looks a bit different, but in general we have these pulses that are very typical for this environment. Now, some devices don't need, they don't have an energy problem. We couple them in the power grid, and we can operate them as long as we have power available around us. But as soon as we want to have some mobility, or build these sensors into rotating or moving parts, or if we cannot put cables to everywhere, then we are reliant on batteries, other energy storage, or that we can harvest energy from the environment. And I'm now addressing both the part about batteries. I'll explain you how batteries behave if we have this particular IoT devices and their behavior, and then how we can actually use energy from the environment not only to harvest and charge batteries, but also to communicate. Now, the first part about battery dynamics is I've done in collaboration with Laura Feeney and Per Gunningberg. And now we have seen already this typical pattern of duty cycling. We are on for a brief moment of time and then we don't put the load on the battery. The batteries, they are complex electrochemical systems which are mostly designed for continuous discharge. And we wanted to study how does the battery dynamics impact the lifetime if we have these particular patterns which are not what the battery was designed for. From literature, we know two effects that are important in this context. One is charge recovery. That is that if you put the battery at rest and don't apply a load, then the battery can recover a bit. You might have experienced that when you had a device that ran out of battery, that if you switched it off and waited a bit, you were able to run it again a little bit later. The second effect is the so-called rate capacity effect. And that says that if you put a very low load on the battery, then you can extract more capacity from it than if you put a very high load on it. And now if we look at from a basic first experiment, we see that if we have a continuous discharge, and let's say the battery holds for 1 day, as just an example of a very small battery, and then we apply a 1% duty cycle to it, so that is only 1/100 of the time we use it. That does not only give us 100 days of battery use, it actually gives us up to 300 days. So there's a factor of 3 that, of battery life extension that we want to now to look, why do we get that? Now, the basic questions that we wanted to answer is, does the pattern matter, the load pattern? And to answer this question, we distinguish between two cases addressing these two effects, the charge recovery and the rate capacity effect. And so if we assume the same average current, so over the time, if we take the average of we apply, then we can do the patterns in very different ways. On the left side, for the charge recovery effect, we use the same load, but either very brief and frequent loads, or a little bit longer and less frequent loads. But in average, they are the same. To test the rate capacity effect, we vary the load, so how many amperes we drain from the battery. We can either drain a lot during a very short time, or we can drain a little bit less over a long period of time, which is illustrated on this side. In the experiments, we choose an average current of 300 microamperes that corresponds to a typical load that we see on battery-driven IoT devices with a duty cycle that we choose between 1% and 5%. And we took a lot of batteries to do statistical analysis on them. We built a test bed where we can put a number of coin cell batteries in these cards. And then we can control exactly at what time that we apply what load. We put them in a rack and let the experiments run. Now if you have a load in average of 300 microamps, ampere, you can imagine that an experiment with these coin cell batteries take quite a long time. And in fact, these are experiments that took 6 to 8 weeks to complete, to drain the whole batteries. If we look at the results, now here in this graph, we see on the x-axis the consumed current. So instead of time, in order to compare different loads, we took here the capacity that we drain. And on the y-axis, we have the voltage. And we see immediately that the battery reacts differently in the response to a load depending on how big the load is. So if we have a small load of 120 ohms, we get down here of 4.2 milliamps. We only drop to this level here of about 2.85 volt. But if we apply a current that is maybe 25 milliamps, that is about the maximum that you need to communicate on an IoT device, then we drop much more. And now this, both the red and the blue line, they have a load of 25 milliamperes. And we see already there's a big difference in how we apply that, whether we apply the load over 600 milliseconds or if we distribute it over 25 seconds and do it much less frequent. But in general, we see this pattern that we drop, then we stay constant for a long time, and then only about after 70%, or when about 30% of the lifetime is left, we start to drop considerably in the voltage and very quickly. That is what you often also see in the mobile phone charge gauge that shows you you still have 80% and then suddenly you have only 20. So this is, they have now also improved over time, but at the beginning you might have experienced that. Then we should also be aware that the electronics that we have on these devices, they stop working at the cutoff voltage, usually around 2 or 1.8 volt. If you go below that, the device stops to work. In another experiment, or the same results but presented differently, we have now on the y-axis the time average current that we apply. So on the left, we have a very low load, and on the right, we apply a higher average current. That means we maybe stay on longer or we apply a higher load. And the different symbols, again, represent how big the load is. We vary between 1 milliamps and 25 milliamps. And it's not so important to judge now exactly all the details of this graph. It's a lot of information, but what is essential to see is that for the same average current, but with different patterns, we get about 15% difference in lifetime of the battery. Now, to better understand, we looked also a bit into battery models, and I give you a brief overview to give you maybe a little bit the intuition how a battery works. And one of the most accurate model is, of course, if we can model the electrochemical behavior of the batteries. If we know how the electrons and the ions flow in a battery and affect the chemical processes, that should give us quite a good answer of how a battery works if we have a good model. Then there are a few simpler models that are much more intuitive. One is some are inspired from physical processes like kinetic battery models, and then there are also models that are based on electronic circuit designs. The electrochemical simulation, as I said, simulates or models how the ions are transported from the anode to the cathode and make chemical reactions with now the lithium manganese that is in these batteries, in these coin cell batteries, and at the same time they release electrons that will flow through our load. There are models or simulators that, for example, the Battery Design Studio that we can use that have models of a large range of different batteries, among them out of the coin cell battery that we are using. It's efficient for continuous discharge, but if we now have to apply millions of these very small loads, these models have to calculate a lot, and the simulation takes much longer time than run the experiment on real batteries themselves. the kinetic battery model, here I want to give you the intuition of why the battery recovers a bit. So we imagine that we have two wells that are connected through a small valve here at the bottom. And from the laws of physics, we know that if we have a difference in the height in these two wells, they try to equalize. So there's some liquid flowing back and forth there. And now the model assumes that we have a well of available charge from which we draw if we apply a load to the battery, and a bound charge which is not available immediately. So if we now apply a load here, we start to drain on this side. At the same time as we start to have a level difference, that makes also that we have some amount flowing back from the bound charge to the available charge. If we look on this side, we can express the differential equation that we have here, depending on the difference of the height, a flow from here to this side. Now, if you solve these equations, you can parameterize it with experiments from the battery. You can get quite a good understanding of how it behaves. One example is, for example, if you apply a very high load, then you drain this much faster than the bound charge can flow back. So you will basically deplete the battery very quickly, and then when you put it at rest, the levels will even out again. Then you can take another load and continue with that, and this way continuously go down and use up all the bound charge. The equivalent circuit model is the simplest, and it doesn't model how much charge we have in the battery, but the response of the battery to a load. Typically, as I have already seen, we have an immediate drop in the voltage at the beginning when we put the load, and then it continues to go down. We have some transient response that then gets more or less constant over the load, and when we release the load, we go up again and have this transient response. And this is modeled with the resistor that is responsible for this drop, and the transient, slow and the fast response that are responsible for what happens here when you apply or release the load. Now these parameters, they change over the lifetime of a battery. For example, if we look at when the battery still is almost full, 75% of charge is available, we see that we have here still quite flat when we apply the load. Then it goes up, and this time process is rather quick. If we have the battery already almost depleted and only 25% of the load left, we don't see that this flat bottom. We see that it continues to go down in the voltage. And the process of recovering is getting much slower. So for that reason, we have now seen that the kinetic battery model with the two wells, which we can use to model how much capacity we have left in a battery, and the voltage response we can model on the transient response we can model with the electronic circuit model. And usually we combine them together to based on what the result of the state of charge tracking, we choose the parameters of the transient response. Now these models have all advantages and disadvantages. The advantage of the electrochemical model is that it can model the rate capacity effect very accurately. Unfortunately, it has troubles to track the charge recovery. The physical processes, or this kinetic battery model, are the opposite. They can model the charge recovery, but not the rate capacity effect. And then again, the circuit model is better at the rate capacity, but the big difference is also in the time that these models need to execute. When we talk about seconds and minutes here, very easy computations, we still have days of execution for the very accurate electrochemical model. Now the conclusion is that if we now know how the batteries behave and know the battery dynamic, we can actually build not only energy efficient systems, we can build battery aware systems. And the difference is, it's not about the coulomb that we drain out of the battery, but in how we apply the pattern, the load pattern to the battery. So we can start to do some optimizations and do load alignment. That is a technique that is also used on our microprocessors. They try to align all the operation during brief times. When they have high clock frequency, then they go a little bit down and save energy to optimize the battery lifetime in our computers. But if we now have an IoT system as a distributed system, it's not only about ourselves, our device. We also have to take into account the interactions with other devices, because if we have to communicate with another device, we have to stay awake until this other device is there, or synchronize and then communicate with it. So we have also to do some cooperative sensing, or try to align among diverse devices. Then we have also to take into account that we should balance the load in the system. Not only one device does a lot of work and others do little. As we have a lot of redundancy and maybe several sensors cover the same area, we can maybe do a round robin or another strategy to even out and balance the load better in the system. Then finally, by looking at these particular patterns, the transient response of the battery, we can also learn much more accurate about the state of charge that we have left in the battery, and as an input to the load balancing algorithms. So in summary, we have learned now that it's important that we give the batteries a rest. We have seen that very brief loads, but with a high load, are much more beneficial for the battery lifetime than very long but low loads. The difference is about up to 15%, and with this knowledge we can build much more efficient Internet systems, or Internet of Things systems. Now, what is better than use a battery most efficient? That is not use a battery at all. And this work is done together with Ambush Varshny and Timo Vogt. And we know already that we have a lot of energy in the environment. We are used to harvest sun, flow, movements, vibration, temperature gradients, and so on, that we can use to harvest energy and charge batteries. Now we can do the same for communication. Here's a simple example to illustrate this. We have, instead of using our own lamp and put power into to switch on the bulb and switch off to transfer information, we can use the light that is in the environment and a little mirror to reflect this energy that can be perceived by the receiver. And now exactly the same we can do with radio frequencies. Instead of the sun or a light source that is away from that is in the environment, we can use radio signals that are now everywhere around us. There's radio, there's TV, there's the cellular systems, there's Wi-Fi. All this energy we can use to reflect with an antenna. We put this antenna either in two states, in a state in which it reflects the energy or in which it absorbs the energy. With that we can modulate ones and zeros and transfer information to a receiver which can detect that on it's an antenna. Now we distinguish between two scenarios. The one is the bistatic backscatter scenario that I just described, where we have an external energy source that is only providing the energy. We modulate the information on our backscatter tag and transfer it to the receiver. The other approach is to the so-called monostatic backscatter, which uses, instead of this energy source just providing the energy, it acts also as a receiver. This is very similar to RFID systems that we know very well at the moment. So in this situation where we also modulate information, we call this also computational RFID for that purpose. Now if we look at the signal strength and the consequences of the choice of which strategy we should use, we see that in a monostatic situation, we send the data, the energy from left to right. We know that the energy drops with the square of the distance. But then as the reflection has to go back, again we have a drop in the square of the distance. So in total, we get quite a rapid drop in energy, which makes a very short communication range. In the bistatic model, we have the distance, a drop in energy between the energy source and the tag, and again between the tag and the receiver. But this leads to a very interesting property. We look at this equation with D1 and D2 here, that we have very good reception or energy if we have this tag either close at the energy source or very close at the receiver. So in some scenarios, it might make sense that we have artificially put an energy source close to the sensors where we deploy it. Maybe we put the sensors in the wall or hide it in objects. Then we put an energy source close to that location, and then we can receive it still in the rest of the room. In other scenarios, you might have this energy source far away if it's a TV station or a cellular system. But then if you want to, for example, receive with your mobile phone, you can get close to these sensors, let's say a few meters, and still get the data, even if the signal already is very weak from these TV stations. Now, the first paper, very seminal, was suggested at CCOM 2013, the ambient backscatter system from the University of Washington. And they simply applied this reflection and absorption of energy. And in this, we see here that this is the signal, basically the TV signal, with the backscattered information on top of it. And from this, we can not see what data is sent. So the receiver needs some complexity to average the signal, basically take away the noise. This is done with an envelope detector and then some threshold circuit in order to, then you're left with this signal where we already see the ones and the zeros. Then we have to use a threshold detector to decide whether it's a 0 and a 1. So the challenge here is the self-interference. If now the backscatter tag generates a very weak signal, usually much weaker than the TV signal itself, that introduces a lot of self-interference in these systems. And as a result, the first systems that were proposed, they only had a very low data rate in the order of bits per second, so not kilo or megabits per second, and a very short range, maybe a few feet over which we could communicate. Now in our system that we call LoREA, we did a trick to mitigate this self-interference. And the way we do it is that instead of absorbing and reflecting every bit, we actually apply a high frequency or reasonable frequency for zeros and another frequency for ones. So By this, we can use a mixing process in the radio system that helps us to shift the signal in the frequency space with the delta F, which is the frequency that we use to communicate, for example, for the 1. And that allows us now to shift the energy or the signal from the TV away from this original signal into a band that is adjacent, but where we don't have interference from the original source. And by that, we can then use custom receivers that can do a frequency shift keying modulation, for example. In frequency, it looks then like this. Without backscattering, we see that the carrier at 2.4 gigahertz looks like this. We still have a bit of side lobes which generate, but the further we move away from this central or carrier frequency, the less self-interference we have. At the same time, the further we move away, the more energy we need to do that, because we have to apply this delta F. So we settled for a shift of 2 megahertz, where we still get about for 50, 60 dB suppression of the self-interference, and we see then these peaks appearing here, and that is the backscatter signal. Now the tag to do that is very simple. What we have here is we have 2 oscillators with 2 different frequencies to do the frequency shift keying. Then a multiplexer to choose whether we should use this for the 0 and this for the 1. And then a switch which basically shortcuts the antenna to absorb or reflect the energy. This we have built on a very small tag of this size, and this tag only takes 70 microwatts. That is basically the most energy is used to create these oscillations. If we compare that to regular 2.4 transceivers, typical ones that are used on the sensor nodes that you might have seen in wireless sensor networks, they are more than 10 milliwatts. So that's almost a factor of 1,000 or maybe a few hundred lower than what we are used. And 70 microwatts is also in the order of the energy that we can harvest from the environment. So by being able to communicate with very low power, we suddenly open up to much better alternative energy sources than batteries. This was not possible with traditional radio transceivers. Now, to test our system, we wanted to see how far we get. So we took a carrier that generates a sine wave signal. We put that 1 meter away from, we placed the backscatter tag 1 meter away from it. In this setting, we see here, this is the energy source. This is the antenna of our tag. And then we just walked in an open field, tried to see how far can we get until we don't receive anything anymore. And the results were quite impressive that in 2.4 gigahertz, we get almost 300 meters. And in sub-gigahertz, over 3 kilometers. That is about the range that you also can achieve with transceivers. So we are not much worse than with traditional transceivers that use high energy. We can do further improvements for the robustness in using forward error coding and direct sequence spectrum to make the signal a bit more resistant against the interference that we have around us. This doesn't only work outdoors, but also indoors, which is usually more general, challenging for wireless transmissions. And we were able to send our signal from one room to 1, 2, 3, 4, 5, 6, 7, 8 volts, and still have a reasonable bit error rate of about 10 to the power minus 3 in the 30 meters distance. That is also comparable what we have with wireless transceivers. Now, we use the distance between the carrier and the tag of 1 meter, which is of course very close. As soon as we go further away, for example, in this example, 6 meters between the energy source and the tag, we already get much higher bit error rates. So there's still work to be done here. Now with this LoRa approach of shifting the frequency, we can also do some applications or some nice, apply some nice features, like we can generate frequency diversity. If we have sources that have different carrier frequencies, for example, in this case, 3 different carrier frequencies, and we shift then all 3 of them, we can have receivers on different frequencies. And as you know, that the propagation is frequency dependent. If we have interference on one frequency or a fading on another, we still might get the signal on the 3rd one. Then we also did a whole backscatter system where we placed multiple carriers and multiple tags and were able to communicate simultaneously by using different shifts. Now there are also other initiatives. It's a very hot topic at the moment at conferences. One or a few seminal papers or systems, mostly coming from Stanford University and University of Washington, they try to make backscatter more applicable. We still use a regular transceiver, but they try to shape the backscattered signal such that it can be received with a mobile phone or a Wi-Fi receiver. And here the key message in this paper from 2016 was that these devices, the backscatter tag, they do basically the digital baseband operations, while the power-consuming RF functionality is delegated to a more powerful device that we can plug into the wall. Very similar, the hitchhike and the interscatter system, where the originality here is that we have a Wi-Fi signal and a Wi-Fi receiver, and they try now to change the Wi-Fi signal that encodes information such that the receiver receives the information that the tag wants to commit and not what the original sender did. And then likewise, it's possible to translate Bluetooth signals into Wi-Fi signals. So that's a lot of engineering work that has been done, suggested by these 2 groups. And then the last trend that we see is now, instead of measuring something and then translating it into this frequency to shift the signal, we use the physical process that we want to measure to automatically drive the backscatter. For example, if this wheel spins, it flips the mirror faster than if it doesn't spin. So then at the receiver, you can detect what is the frequency of the ones and the zeros, and calculate back into how fast is this wheel driving, for example. Then there are also attempts to use analog backscatter to generate FM signals that we can receive with radio transceivers or radio receivers as we listen to radio stations. That can be very useful, or application scenarios are that, for example, posters or cars or T-shirts or whatever smart objects can generate FM signals that we can understand and listen to. And then you might have heard or see the big buzz about the battery-free cell phone, which would be the dream for many of us, where they implemented basically the voice encoding with using FM backscatter to transfer voice information from this device to an FM receiver that you can receive. Now, as we can communicate very cheaply, it's not necessary that we do all the filtering and compression and coordination for the communication on a computational block. Sometimes it might be much more efficient to just send it, because computation is now in the same order as we maybe used to communicate, and which would simplify the design of this text considerably and also the price. Here is a list of state-of-the-art backscatter systems. And as we talk, there might already be a new one. This list is from 2018, but there now, research groups are now coming up to speed and proposing new ideas all the time. And all these systems have different strengths and weaknesses. Some, they try to get very high bit rates, but the range that they can achieve is very small. Our approach was maybe a little bit less bit rate, but longer ranges, and we see everything in between. Some also use customized hardware to get up the power that they need, the processing. They implement the functionality in FPGAs or ASICs, also to come down with the power consumption, and so on and so on. So to conclude, I think there are big opportunities that in just a few years, we will be surrounded by thousands of devices. With that, we can build the smart cities, the smart cars, the smart factories, and whatever we have heard about also in this conference. And in some situations, charging batteries might not be an option to do, either because the devices are not accessible, because there are too many, or because it would be too expensive to have human labor going there and exchange batteries. But I'm now not advocating that battery-free is the solution. I think I want to give you the message that in some situations, when you need performance, reliability, and have to do complex computations, then we cannot avoid to use batteries. I have shown you and give you a little bit of tools to implement battery-driven systems more efficiently. Now on the other side, if you want to have infinite battery life or lifetime, keep it simple, maybe put sensors into objects which we cannot connect or built into walls and bathrooms to detect other things, then battery-free is an alternative which enables new types of applications. But when I say battery-free, that doesn't mean that we don't have an energy source. The key idea here is just that we move the energy source away from the object itself. We have some separate energy source, either it's light or RF energy or something else, that powers or that we can use and reflect on the IoT devices. We are very power efficient with low load. Okay, with that I thank you for the attention and again for the invitation to give this keynote. I can also mention that in Uppsala we have a few students from Sri Lanka that are working with us, and it's a great pleasure now to be able to come here and learn about where they are coming from. Thank you.
Thank you. I have a couple of questions if possible. The first is about the first part of the presentation where you talked about the battery behavior. So you mentioned that you can optimize battery duration by consolidating basically tasks at regular intervals, but that you can also, if you have a fleet of Internet of Things devices, let them cooperate to optimize the duration of all the batteries. Mm-hmm. So can you elaborate on this? So how can you let them cooperate in a peer-to-peer fashion, or you assume, or is there any central point of organization? So this is a point that I would like to.
So the ways that you have to coordinate among is when you do an interaction. You can use that as kind of a point of synchronization, then maybe to self-synchronize the system over the time if you want to. If we would synchronize everything, everyone would wake up at the same time and then go to sleep, then we would have a lot of contention during this small time period. But now the state of the art in now distributed wireless sensor systems, for example, is that we have this asynchronous wake-up protocols, where if you want to send something, you send it repeatedly until the device that you want to talk to wakes also up. Then you exchange the information, but then from this point on, you can change your schedule to adapt to maybe be awake or have the higher probability to be awake next time at the same time again.
Okay, good. Second question is linked to some engineering aspect that I don't know personally, but so you said using this backscattering technique, you are able to exploit the energy you already have in your environment. But is it also possible to catch this energy and use it for sensing? So is the power enough to do it? So catching energy from a Wi-Fi and give this power to the sensors.
Yeah, harvesting from RF signals is, given that this energy already is quite low, is not so efficient as was using, for example, a solar cell. That's very unfortunate. So, for example, we tried to harvest from 4G systems, and we saw that already a solar cell of this size gives us more energy than what we can get from Wi-Fi signals. But it depends, of course, also how close we are to the Wi-Fi access point. Maybe here I can get,
I see.
It might be sufficient to power my sensor, while over there it might not.
So if you live close to a broadcasting system, you perhaps can do it.
Yeah, it depends on the distance. But we can also harvest over a long time. Let's say we want to measure something every hour. Then we have an hour to harvest, and then use this little energy briefly to do a measurement and send it.
Okay, thank you.
So I feel that batteries seem to have a tendency to run out when you need them the most, which is a terrible experience that we have all gone through. Professor Ruhner, thank you so much for an extremely interesting and useful presentation. Now it is time to felicitate the keynote speaker. For that, may I cordially invite Professor Nihal Kodikara, Senior Lecturer of UCSC. Thank you very much, Professor Kodikara and Professor Ruhner.